today I'll talk a little bit about some ideas and the things that I had related to concepts, one of the largest features of C++20. Okay, so basically C++ concepts are here as of C++20. We can be very, very happy. Here's a short video from 2014. Those of you who don't recognize the person here on the screenshot is Alexander Stepanov. He's the guy who wrote the STL way back then. And let's see how he thinks or what his class does with concepts in early 2014.
Okay, so we have a whole bunch of concepts that we've used in all of our code, and these are all defines to type name, right? It's just documentation today. Maybe at some point there will be a way in the language to express this, but today that's the way it is.
Okay, so as you can see, in 2014 there was no concept in the language, but still library implementers, they were thinking about their libraries in terms of concepts. They had these defines to just change the word type name into different concepts, and they sprinkled concepts all around their library code because it made it easier for them to think about their algorithms, think about how they write their code. So that was 2014. It seems early, but actually concepts were considered in the language in C++ way, way earlier. Here's a talk to the same forum, but a year earlier by the inventor of C++, Bjarne Stroustrup, again about concepts.
Concepts are fundamental. They're meant to represent fundamental concept in an application area. Alex has been saying this for at least 15 years, but most people haven't gotten it.
Okay, so at least in 2013, most people haven't gotten it, didn't understand that concepts are fundamental. That's what Stroustrup is telling us. Hopefully by now, people got it, and that's why we see it in the language. So in this talk, we'll try to understand what is it to get, what's important about it, and how do we use it, and how did we live without it. So concepts and template metaprogramming, to some extent, go hand in hand. So let's discuss that a little bit. Basically, templates, as far as we understand, we know that we have templates classes, templates functions, many template things in C++. Here's a small example of a template algorithm in C++, the min algorithm. It takes two objects of the same type and then returns the minimal one out of them, okay? It's a template, and that means that the same algorithm can be used for many, many types. Every type for which I can take the greater of or less than operator, I can usually implement a min for, and these 4 lines do it in STL. Metaprogramming gives us even more power. It lets us implement different algorithms and overload them, okay, such that the compiler knows to choose the correct algorithm with the same name. Okay, so here's another example. We can see the swap algorithm. Okay, it's also from the STL. Swap algorithm is defined for any type T. Okay, we can take 2 references and swap them. There's also a specialization for arrays of type T2 of size n, which actually are implemented as a completely different algorithm. If we were to try to run the first algorithm on 2 arrays, we'll probably not get what we wanted. We'll probably get something like a shallow copy, while we would expect a deep copy to happen. Okay, so in this example, we can see that we use template specialization as a type of metaprogramming to let the compiler and the language choose which of 2 different algorithms to implement for the same name, for the same overloaded name. In this case, if the compiler had made a mistake and gave us the wrong algorithm, the results would be very, very different from what we had expected. Okay, there are other cases, by the way, where the choice of the correct overload is not a matter of functionality, just a matter of performance. Okay, so this is a very, very long and convoluted piece from STL. I won't go long about it, but basically it's the implementation of, it's an internal implementation of the fill STL algorithm. Okay, that basically wants to accept 2 iterators, the first and the last, to arrange and the value, and it tries to fill each item in the range with the same value _ C. And in this case, there's usage of a metaprogramming technique called the enable if. And using enable if, they created a specialization, a specific implementation that just uses memset. Okay, if the STL implementer had decided not to do this type of metaprogramming, and probably everything would be fine in terms of functionality. Though I assume that a typical fill implementation that just does a for loop and assigns a C to each and every element would have worked functionally. And to a large extent, one might expect an optimizing compiler to convert it into a memset by itself. But here, the STL implementer decided to use the enable if mechanism in order to force the compiler to use a memset. Okay, so that's a little bit of a taste of the way that concepts and the libraries can be used in order to choose among the different algorithms for the types that we want to apply the algorithms on. Okay, so here's a short agenda of what we're going to talk about today. It's all about putting the right constraints on our templates. Okay, having template algorithms and making the compiler choose the right ones for the right types. We will see how C++ concepts let us do it, and also see other alternatives, mainly older ones from older types of language. I will tell you a lot about what I think of the various things, a few facts as well. But whatever you hear, you know, I have a little bit of experience, but I'm not. You might know more than me. I'll be happy to hear what you think about those things as well. I'll try to give a few ideas, a few tips about which mechanisms we should use, when are concepts the right thing for us, when are not, as well as I'll touch on places where I think the language itself can be augmented, can be improved. In this talk, you'll see many code snippets from the STS itself, like we've seen so far, as well as many clips from YouTube. Okay, so let's get going. So first of all, let's get back to that talk by Strastrup, where he will tell us all the way from 2013 what concepts are in his words. Okay.
And the thing we were working on is it becomes a bunch of constant expressions. It becomes a bunch of Boolean expressions. Does this type have this property? Does the argument type has this property? Has the combination of types we get as arguments got this property? It's all predicates. It's all Boolean algebra. There's nothing about scopes, nothing about objects, nothing about indirect jump tables. It's all Boolean expressions.
Okay, sounds quite simple, right? All Boolean expressions, just a bunch of Boolean expressions. That's what it is. Okay, and what is it? Sorry, what is it good for? Why would you use concepts in C++ if we ask Strastrup 7 years ago?
You can overload if it meets the sets of constraints from one and not the other. That's the story. If they are subsets of each other, then it'll take the one the biggest one it can. In other words, if you most specific, well, the one that meets the largest number of the predicates.
Okay, so the basic idea is using concepts for overloads. Okay, we have various overloads, and the compiler will choose the one with with the largest number of predicates. Sounds simple. Sounds cool. And let's leave Strastrup alone for a minute and show you a little bit of text. I won't read it all, but these are the first few sentences in C++ reference talking about the concepts library. It's quite concise, quite succinct, but I won't go through it all. I just want to highlight two sections that talk about semantics versus syntax. Okay, so C++ concepts, they give us various constraints and various ways to think about the syntax, what's well-formed and what isn't well-formed. But actually, it's not just about that. It's also about semantics. Okay, most concepts in the standard library is not just what methods and how can they be used syntactically, but also about the semantics. And down at the bottom, we can see that if a semantic requirement is not met at the point of use, the program is ill-formed, no diagnostic requirement required, which is what we all love to call undefined behavior. Okay, so the fact that something looks syntactically like the right concept, the compiler is allowed to try to generate code for us, but if the semantics are wrong, then it's our fault, and we need to deal with it. Okay, so whenever we think of concepts, we need to remember it's not just the syntax, it's also the semantics. Okay, so this is all that concepts are about from my perspective. Okay, so it's just a bunch of Boolean expressions, and we use them in order to take the overload that meets the largest number of predicates. That's the way Bjarne said it. And when we design and build our concepts, we think about the syntax, but also about semantics. Okay, so now we'll dive in at these three attributes of the concepts. Okay, so first of all, a bunch of Boolean expressions. Very, very simple. Here's a nice concept, integral. Okay, so integral is basically just a Boolean. Here I borrow from an older version of C++. Is integral t is a type trait, okay, which is also a Boolean. And here I just take the type trait and convert it into a concept. Nice and simple. Okay, let's make things a little more complex. We can create concepts with Boolean expressions as well. So we have the integral, and now we can use the ampersand operator, combine it with another type trait, and we can create use ends and the ors as much as we like to create more and more complex concepts. As we seen before, there's the notion of counting how many predicates are within a concept, because the more predicates I have, it means maybe that I'm more specialized. Okay, and the third interesting way to write a concept, very, very new to the language, looks revolutionary, is the requires expression. Okay, so a concept can be, we can define it using requires expressions, where I basically can write some code. The code isn't actually executed, isn't actually being turned into assembly, but it just checked for whether it's well formed or not. So in this case, if I take two references of type t, and it's legal in the language to do a ranges : swap on the two of them, it means that this requires expression is true, and the concept swappable is true or is satisfied for the class t. Okay, so these are the three basic ways to write concepts. Okay, it can be just Boolean expressions with the operators, and we can use the requires expression. This is all very nice, very, very simple. In fact, it's so simple, a lot of it was in the language even before C++20, right? So as we've seen, type traits, they're old in the language. There's a full header file in STL called type traits. Here's a few lines of code from that header file. A bool constant is something that that has that is templated on true or false, and any type trait can derive either from true type or false type if it's a Boolean type trait. And that's the way that we used to write these Boolean expressions on types before we had C++20. Actually, in C++14, if I remember correctly, there was another way to do these types of Boolean expressions on types, which is variable templates. Okay, so this is something that is actually from the C++20 standard, like this specific line. But even ever since 2014, it was okay to just declare Boolean variables, which are const expr, templated on type t, and we can give them a value of either true or false, and have Boolean expressions or bunches of Boolean expressions on types similar to concepts. Nothing new, nothing special, nothing to write home about. And of course, operators were also allowed. Here's the way that the is-scalar type trait is typically implemented in the STL standard. It's just a Boolean operator on other type traits. Again, nothing too fancy, should be relatively easy to understand. And so many things that were possible for concepts are also possible before that. Let's talk a little bit about the requires expression and whether we had this requires expression capability before C++20. Okay, so basically we didn't really have this word. This is a new keyword in the language, but we did always have sphere, right? I assume many of you know this acronym, that substitution failure is not an error. And SFINE lets us do things with metaprogramming that are very, very clever and tricky. And here's an example of defining this Boolean trait called has meow, which will be true if type T has a method called meow that accepts 0 arguments. Okay, so I won't go over about the magic of void T. It was added to the language in C++17, but you could write it yourself even before that. But it was a way to do something similar to a requires expression even before C++20. Okay, so I want to create a concept of meow. I could do it even before we had concepts. Okay, so the basic way to create concepts, the basic schematics were already in the language. Not only that, if you wanted to create Boolean expressions over types, we had even more ways before concepts, and we still have them. Okay, so what are such some examples? So first of all, specialization. Okay, if I want a trait that tells me if something is const or not const, I can use partial specialization and have a basic is const being a false type unless I partially specialized for every type T the constness and get the true type. Okay, this is something that is not part of the C++ concepts, but it was always done with based with structs and the other types of templates. Another similar thing is using a template specialization, not with a partial specialization, but as a mechanism, a way to do a opt-in and opt-out. So this is the example that I gave a few slides ago about the enable borrowed range. Okay, it's, as you can see, it's a template variable from C++20 that is, from the STL standpoint, it's always equal to false. So, but the thing is that for every type that a user writes, a user of the STL, we ourselves, for every type or class R that we write, we are allowed to go and specialize it. Okay, and we can say that for my specific class, enable borrowed range will be true. Okay, and this is a way for me to opt in to some behavior if I want. Similarly, there are other uses where like a general Boolean will be true, and I will be, and the user of a library will be allowed to specialize and opt out of specific functionality. Okay, both of these things are part of the language, but they are not a part of concepts. Okay, in C++20, you cannot do concept specialization. Okay, you can do a class template specialization, you can do function template specialization. You cannot do a concept specialization. Okay, I don't know if it's an oversight, if it's fully intentional. Perhaps even maybe I'm wrong, but that's what Goldbold showed me. But anyway, it's not very important because as we saw, we can define concepts based on type traits. And if my concept is equal a type trait, then a user of my library can just as well specialize the type trait, and my concept will be as good as if it was specialized. Okay, and last but not least, another a way to define a bunch of Booleans or expressions is via traits classes. Okay, so here's an example. The numeric limits is, I think, a traits class that many of you probably know from the STL, where all the numeric types, the integral, the floating points, etc., had many attributes, both Boolean as well as value types around them. We can get the minimum, the maximum, and all various things. And it's perfectly legal and perfectly fine if I write my own class that is numeric to go ahead and specialize the traits class for my own class. For example, temperature. I can say that my temperature does not have infinity, for example. Okay, the rules say that I'm allowed to specialize on my own class. I just need to make sure, both, first of all, to be semantically correct, and secondly, I'm expected to implement all the traits inside numeric limits. I can just go and implement part of them. Okay, so this is basically a summary of various ways to create a bunch of Boolean expressions over types in C++20 and before. Okay, so this I think is a reasonable place to stop for questions. So yeah, I don't know if there are any, if anyone wants to ask something or have a comment.
Can concepts be created from other concepts?
Yes, the answer is yes. In the example that we've seen a little earlier, we actually saw an example. You can see that the integral concept was created in the first line, and sine integral is now is the integral concept along with an extra refinement. Okay. Great. Any more questions? Cool.
Are concepts generally much faster than Svine?
Yes, they are. I'll talk a little bit about that, but definitely one of the strong points of concepts when using them and when letting the compiler use them is that the compiler will usually be faster when deciding on the overloads using concepts, as well as much nicer when it comes to error messages. Okay, so our error messages, in case none of our overloads meet the criteria, are usually much easier to parse, easier to understand. Okay, I'll talk a little bit about that in the next section. Okay, let's move on. So now we'll talk about the ways that we actually ask the compiler, ask the language to help the library writers or the users of libraries to choose between different implementations of algorithms, take the best one. Okay. Again, we'll see how it's done with concepts and how in other ways that we could have used before that. Okay, so the main way to do these things with C++ concepts is using the requires clause. Okay, so don't confuse the requires expression from the previous chapter where we created Booleans and attached them to concepts with the requires clause. Requires clause is what we would put right after a function or a class, or I think also I could put requires clauses on variables, on all different types of templates in order to constrain and define which specific templates are allowed for this specific function, algorithm, class, etc. There are ways to constrain functions or classes to concepts without using the requires clause. There are actually two more ways. One is by writing a name of a concept instead of the word type name or class inside the angle brackets. The other way is by using the word auto. I won't delve too deeply into it. You can go and look it up. But the requires clause is very easy to see in your eyes, to understand. Hey, this is a way of constraining my functionality. And as we mentioned, the most specialized version, the one with the most Boolean subclauses that meets by criteria, is the one that wins in case I have more than one algorithm or more than one candidate for overload resolution for a specific type. This resolution is Svine friendly, meaning that if any of the candidates isn't well formed, doesn't compile, so to speak, the compiler doesn't see it as an error. They just remove that alternative from the overload set, from the criteria checks, and whichever alternative is left, that's the one that will be used. Just as I said a few minutes ago, using requires clauses and using these concept type constraints will usually lead to better error messages in case there is no match, and will also usually lead to faster compilation speeds. In fact, typically when a compiler needed to check whether a template matches whether a template matches an overload before that, and had to use various tricks like enable if and void t, etc. It meant instantiating many objects usually, and those could take a lot of time. Okay, so that was that's C++20. Let's hear Timur Dumler from just a few months ago tell us a little bit about the ways in which we used to constrain our functions before C++20.
Let's remember let's see if we can remember how to use std enable if. Okay, so you can write the std enable if integral type and floating point type. Where do we put this? This is something that I can never remember, right? So you can put this onto the return type of the function, but then you don't really see the actual return type anymore, so that's not great. You can put this into the parameter list, but then you don't really see the parameter list anymore. So I don't like either of these. So my favorite method is actually to put this into the template argument list, because then you can still cleanly see the function signature. So that's, I think, the most readable way of doing this, except it doesn't work. Because it turns out that in C++, defaulted template arguments are not part of the function signature. And then you again have the same function signature twice, and then you again get this error, redefinition of function template. Turns out you can work around that because that rule doesn't apply to non-type template parameters. So you can make this an int template parameter.
Okay, so very, very convoluted, very, very complicated. It was all possible before C++ 20. There were many ways to do it. None was very nice. None was very simple. And each and every library developer needed to find out their own way, which was nicest for them, which was the best for them. And the C++ 20 obviously makes things much simpler for us. Okay, but this wasn't the only way. Enable if wasn't the only way to constrain things. Let's discuss a few more alternatives that were possible and were used for both for constraining different overloads and also in general to have like interactions between a library template code and the user code, the application code that has the actual objects that we want to instantiate our library with. Okay, so first of all, as we talked about even before around the traits, there's specialization. Okay, we saw this swap example before. Very similar to the way that C++ knows how to choose the correct concept with the most that is most specialized. C++ also knew from day one how to choose the best specialization that is most specialized. So C++ knows that this second swap is more specialized than the first one, and for that reason, if both of them are possible for a type, C++ will choose the second one. Okay, and that way, a library can dictate which of the user's classes goes to one alternative versus the other. Okay, another way to interact with user code is regarding customization arguments. Okay, it's not quite as powerful or not similar to the constraint thing, but it's a way for me to interact with user code. Okay, so in this example, the max element algorithm, it can work with any iterator type, any forward iterator type that iterates over any object. And basically, if you just try to call max element with your own type, all you need is to have a std : less implemented or working for your type, which means that you have an operator less than implemented for your type. Moreover, if you like, you can go and specify your own comparator if you wanted to look for max element with a different criteria. So that's another way that library implementers used in order to communicate with their users, with their types, and let them interact with the algorithms. So it's not like choosing between various algorithms, but obviously within a single algorithm, I can go and consult with the comparator, etc., and work a little differently. Okay, one interesting, I guess, special behavior of this type of customization is that it allows the caller to override the specifics at the specific call site. So I can call max element 3 times on the exact same iterator with the exact same value type, but with different comparators. Okay, up until now, all the ways that we saw were done based on types themselves and at compile time. And it was just an interaction between the library, which is templated, and the types that they were passed on. And there was no real way to have the same algorithm with the same type, basically using different overload sets or different behaviors in different call sites, in different places in our code. Okay. One other alternative, which is a hot topic of discussion around the C++ standard lately, are customization points. Some of them are recently called the niploids, or there's a customization point that is becoming more and more popular called tag invoke. And here's a link to the YouTube talk about tag invoke from the Core CPP meetup in Israel, where again, a library can tell or let the users of the library choose how to customize and how to it can basically inject code into their own algorithms based on the specific types that the algorithms use. Okay, so that's another option. I won't talk about customization points a lot. You can look it up. It's worthy of a talk on its own. Okay, and last but not least, I want to talk about another method which is called tag dispatch. As you might remember, it's part of the title of my talk, which is the STL classic way of choosing between implementations. So here's a short example that will hopefully make everything clear to us. This is the implementation of the advanced algorithm from Iterator header. Okay, advanced is a very, very simple algorithm. It takes an iterator and a length, and it basically wants to move the iterator forward n steps. Okay, so I want to move the iterator forward n steps. And the thing is that different types of iterators have different algorithms that can be done. More specifically, random access iterators can just jump n steps in one go. And for iterators, bidirectional iterators need to actually go n steps and call plus plus each and every time. So the way the STL chooses or has the compiler choose the right implementation is by calling this internal underscore advanced algorithm and giving it one extra argument, which is the iterator category. Okay, the iterator category is what we call the tag of the iterator, and this way of calling a function with a different type of argument is what's known as tag dispatch, where the compiler will know based on the iterator category exactly which argument, which type of advance to call. And that's the way it's done in many of the STL algorithms. So, and if you think about it, this is an opt-in type of behavior. Okay, so when the library of the STL library wrote the advanced algorithm, they basically gave the responsibility of choosing which specific algorithm to choose to whoever implements the iterator. Okay, so if I write my own iterator, I need to specialize iterator traits, choose my own iterator category, basically opt in to the specific category or concept that my iterator belongs to. If I did the right thing, if I chose the correct trait or category that matches my semantics, then the STL library, the template library, will know which algorithm to use. Okay, so it's an opt-in type of way. And in STL, this is hidden. As we can see, the advanced method has this double underscores in front of it, and the standard doesn't expect anyone to deliberately call underscore advance on themselves. It won't be a defined behavior to deliberately try and call underscore advance by myself. But this is considered an implementation detail, this whole tag dispatch. But technically, I can tell you that template libraries that use tag dispatch do not have to make it as an implementation details. You can write your own template library and decide to have tag dispatch as an, I guess, declared way of doing your dispatch. And this will basically allow your users to also do a call site overrides if you like. Meaning, if they choose to call your algorithm without specifying the category, then the compiler will take the category from the traits and use it. But whoever likes could go and deliberately call an algorithm with another category and try to see if it works. Okay, because we already saw that sometimes a concept is a subset of another concept, this can sometimes make sense. Okay, there was a talk by Andrei Alexandrescu a few years ago when he discussed the performance of the sort function and the sort algorithm in STL. One of the things that he talked about was that even for random access arrays, there are some cases where maybe insertion sort can be faster than the quick sort. Okay, and for that reason, the fact that the STL library doesn't allow me to directly call insertion sort or the sort for bidirectional iterators on a random access range is somewhat of a shame. Okay, if I were to write STL or write the standard around STL, I would consider maybe making this tag dispatch part of the interface to let whoever wants to use the STL to go and choose other types of tags when they call the functions. They have to know what they're doing, of course, if they use a tag that's not semantically correct, they will get the undefined behavior. That's usual with the STL, right? But that's the way it is, just so you know. Okay, so here's a short summary of the different ways to do overload resolution that we talked about, and a little bit about the differences between them. Okay, so first of all, let's talk about on-off. What do I mean by on-off? I mean, which of these methods can be used in order to just include or exclude a specific algorithm for specific types. Okay, so what do I mean by that? So, for example, I want to make sure that the min algorithm will not be called for objects that do not have STD less for them. So if I use a specialization, the library itself can use specialization and define which types it is specialized for and which types it is not. Okay, so I can have I can write my library such that I'm only specialized for specific types. Similarly for Spine, if I use enable if, the library can write whatever expressions they want in enable if and limit the applications from using or not using my library algorithms. And the same for the C++ concept requires. When I write my library, I put the requires clause around my algorithms, and basically every type that the user wants to pass to me has to meet the requirements. If it does not, then it's off, it's not available, and there's no way for them to call my library with their own types if they do not meet my criteria. Okay, for tag dispatch, as we've seen, is a place where it's opt-in by the application. The application chooses whether its types meet the criteria or not. Okay, they obviously have to be semantically correct, but if they are, they can do it. Even if it's the responsibility goes to them. If they choose to do it correctly, then they will they get all the benefit. Similarly, for nibloids is not really an on-off kind of thing, but sometimes you can do it. If you decide not to define a customization point for your object, it will mean that you won't be able to call template algorithms that need that customization point. Okay, choosing from a few. If I have different algorithms that are viable candidates for a type, and I want to let the compiler choose the best one for me, or I want to let someone choose the best one for me. As I mentioned, both specializations, Spine and requires, they're very, very similar. The library basically says what it wants, and especially for specialization and for requires, the C++ language also defines which is better than what is the ordering of more specialized versus less specialized, or more Boolean expressions versus less. And whatever the library chooses, the language knows to pick the best one. Okay. And again, for tag dispatch, as we mentioned, the application can have its say. I can write a random access iterator and put it on its traits that it is bidirectional, and that is the choice that will be taken. Okay. Regarding injection of user code into the algorithm, so all the different the first two methods of just choosing between constraints, they don't really allow the user to put in their own code inside my algorithm. But definitely function arguments such as the comparator and an nibloid that will let the caller basically inject code into my algorithm. I can just want to say, by the way, that these alternatives and these options are not disjoint. Okay, one can write an algorithm that both uses a requires or Spine clause to choose whether it's viable or not, and also accept a function argument or use a customization nibloid to get some user code injected into it. Okay, in terms of simplicity, it's obviously a matter of opinion and taste, but I would say that Spine is not very simple, not very friendly. Requires clauses in C++20 is very, very easy. It was meant to be a very simple way to do these types of things. Similarly for specializations, we're used to working with them, we're used to dealing with them. Tag dispatch, so-so. I think it's relatively easy for C++ experts, but mainly because they've been here for a long while. Similarly for the rest. If I'm talking about really trying to do advanced uses of these options, things can change a little bit. There are ways to let the application have its way around the Sphene, mainly by using these opt-in and opt-out types of traits. As you mentioned, if I write my code based on some Boolean expression that is always false, but I let the application opt in and turn specialized with the true, then I can use that to with Sphene and requires to give some control to my user on which of different algorithms to choose. And as I said before, if I turn the tag dispatch from an implementation detail into part of my interface, I can basically let my caller even choose which algorithm to go with instead of just making the best choice for them. Okay, and similarly with the function argument and the nibloids, because I inject code into my algorithm, I can do runtime checks, obviously, and call the user's code in runtime and divert to one of a few algorithms if I really want to do so. Okay, so that's basically a little bit of how different ways of choosing between overloads are done for template libraries, and how template libraries can interact with their applications that use them. And this is, I think, a great time for maybe stop and see if we have any more questions or comments.
Hi, Roi. Just one comment. I think it's worth mentioning that concepts can also be implemented in terms of context per functions.
Mm-hmm.
In many cases, that enables much easier to write and clearer code.
Yeah, that's a very good point. Thank you, Andre. Cool. Any more comments or questions? Great. Let's move on to the and discuss not just the syntax but also the semantics. And I start off by giving you two examples that show that semantics are a tricky thing. Okay, these are two samples or two examples from the actual C++ standard from various times in the present and the past. This is code that was vetted for a long time by the committee, and still we managed to get things a little bit wrong. I'm not sure if you, who of you are familiar with these two things. So I don't know if there's anyone that really wants to jump and tell me why do I care about is trivially copyable v of std pair int int? Does anyone know what I'm referring to? Okay, so a pair of int int, you know, pair was in the language since 1998. Pair of int int is just like a struct with two ints, but it just so happens that is trivially copyable is false for a pair. Okay, and here's a little bit of a mailing list for just 3 years ago when someone asked to fix this. Okay, to make a std pair and std tuple of trivial types or trivially copyable types, make it trivially copyable itself. And the answer is basically that yeah, that is indeed the case. They are not trivially copyable because of the way that the type trait is trivially copyable is defined. Okay, is trivially copyable is defined to be false if a class has a non-trivial assignment operator. And for std pair, since 1998, there was a non-trivial assignment operator that had to deal with the cases where the types are reference types and not value types. Okay, so if you want to do an assignment for reference pairs, the assumption is that there's I guess a deep copy going on and not a shallow copy, and that's why pairs of references are not trivially copyable. And just by sheer coincidence, this I guess got the standard pairs of trivial types got infected. They're not trivially copyable, and right now it's an ABI break, so no one fixes it. And this is actually a very important performance, I guess, pain point in C++, because you might know that many of the associative containers in STL and many containers themselves have key value pairs. And if I have a container with key value pairs, and it's very, very common that I want to maybe reallocate, I want to move or copy objects from one place to another. If my pair is not trivially copyable, I find myself calling the constructor and going in a loop, object after object, instead of making much simpler things like using memcopy, knowing that there are no exceptions, etc. So this is a real pain point where, to a large extent, STD pair itself does meet the semantic requirements of trivially copyable. Okay, it's just if the two members are trivially copyable by themselves, the semantics are such that you can do a memcopy. Okay, but the syntactic requirements for trivially copyable, which says that you cannot have a user-defined assignment operator, those are not met. And for that reason, each trivially copyable is a type that is false for pairs. Okay, and that's a shame in my opinion. The second example is the complexity of the size method for STD list. I don't know if what most of you think the complexity is, but in fact, sorry. Let's see. Okay, yeah. So the complexity in the standard was actually defined to be constant only since C++ 11. Okay, so in C++ in 98 and in 03, it was allowed for the STL to either be constant or linear. And if any of you is using GCC, you might go and need to go and check, because GCC used to be linear time until C++ 11, and even since C++ 11, you might want to check your defines, because again, due to ABI stability, you might be compiling your STL with GCC such that the size method for a list is linear time. So be careful. And again, and this is an example of the other way around, where I have a size method, and typically when I have a container and it has a size method, the expectation, the syntactic expectation is that this method should take a constant time, but it's not so uncommon for a person to go and implement their own container, implement their own types, just naively implementing a size method that is not constant time, and they break, and by that way they break the semantics of the syntax that they basically opted into. Okay, and specifically for that reason, in C++ 20, we actually have a concept called sized range. Okay, what is a sized range? A sized range is any object that is a range and also has a size method, or basically you can call ranges : size on it. That's the syntactic requirement for the sized range concept. Okay, what are the semantics of it? The semantics actually call for sized range to be constant time. Okay, and what should I do if I have a class that looks like a container and it has a size method which is not constant type? What am I to do? My semantics are inconsistent with the syntax. Do I have to just ban ranges altogether? Well, the answer is that the standard saw it, understood that it's a problem. So here's the hack that they came up with. Okay, so there's another Boolean constant expression in the STL library called disabled sized range. Okay, which is false. And the definition of sized range says that if your type has support for ranges : size, and you do not want that type to meet the sized range criteria, you have to go and specialize the disabled sized range to be true. Okay, and opt out basically of the sized range concept. Looks like somewhat of a hack, in my opinion. If this wasn't a concept, by the way, if it was just a type trait, or I guess if it was just a Boolean expression that is a template, one could take their own class and specialize it, do specialization that opts out from a concept. But there's no way to specialize concept unless there's usage of these types of Booleans. Okay. Note, by the way, that for some reason, in this case, even the definition itself of sized range does not mention even this Boolean. Okay, it's only in the standard definition. Okay, there's no mention of it here. I'm not really sure why. I can maybe guess a little later on if you ask me. Okay, and here's another example of the opposite direction, where again the C++ standard wanted to define a concept called borrowed range, which is a range that, if I remember correctly, doesn't own its members, doesn't own its data. And here again we see, even in the definition itself, that there's a reference to this enabled borrowed range opt-in mechanism, where which is typically false, and whoever writes their own range can go and opt in. They can go and specialize, choose that their range is borrowed, and basically opt in to the entire concept. Okay, so these are various escape hatches that are needed to be added to concepts, because you can just specialize. Okay, so if you want your concepts to be such that they are friendly with your users, and you know that your users might get their semantics and syntax a little bit off, it might be recommended for you, when you write your own library, to give those escape hatches. It seems that the STL ranges found them useful. Okay, let's look a little bit at a few more special concepts and see what we think of them. First, here's Herb Sutter. Again, I think he's currently the chair. He used to be the chair of the C++ Standard Committee, in his plenary talk from September. Let's see what he has to say.
But now let's look at templates. Let's go back to a simpler version of the example with just one in parameter, but of a templated type. Turns out you have to write this nest of things. Basically, you're saying, if I should pass by value, so I should pass by value if it's trivially copyable and the size is less than something. Let's just say you can make your own predicate here.
Okay, so let's stop Herb right now and talk a little bit about what he's doing here. In this talk, Herb tries to tell us how we can make a C++ simpler than it is today. And this is a nice demo showing what C++ complexity is today. And but what really is interesting from my point of view is that you can see that he implements a few different algorithms called old in. Okay, so there's one old in, there's a second one, and there's a third one. And he uses C++20 requires clauses, okay, in order to choose, or to let the compiler choose which of these algorithms to use for its specific type. Okay, so Herb basically knows about the C++20. He uses requires clause to constrain his algorithms. But interestingly enough, when he defines his constraint should pass by value t, Herb goes and uses a const expr bool. Okay, there is no concept here. Why doesn't Herb define should pass by value v to be a concept? Why does he use const expr bool? I think that's an interesting question. He knows C++20, of course, right? And there can be many answers to that, and I can talk a little bit about it later. But I think it's an interesting question. For one thing, I think it tells us that the requires clause should probably be, even in our code, more common than the concept keywords. Okay, it can be very, very common for us to use the requires clauses and to constrain our algorithms, even if we do not think about concepts. Concepts are probably more unique, more special. We need to think about them a little bit more. Okay, that's one thing. Secondly, like we talked a little bit before, now that Herb decides to define should pass by value as a const expr Boolean, basically gives his users the ability to specialize. Okay, now if I write my own type, which is not which size of is maybe exactly 8, I want to opt in to should pass by value, I can specialize with my own type and opt in. Okay, that would not have been possible with the concept. Okay, so that's so I don't know if I would consider this to be a concept or not. It's a special thing. The language won't let me give me all the power if I make it a concept, so I just don't make it a concept. Okay. You can also see, by the way, here another example of where is trivially copyable v is something that's very important for library implementers, and the fact that the pair does not meet the trait is a shame. By the way, although C++ technically allows specializing every template that you want, type traits in the STL are not allowed to be specialized. Okay, it is undefined behavior to specialize type traits. in STL. In general, I think almost all traits in STL are not allowed to be specialized unless specifically granted. And that's why people who know that their pairs semantically can be trivially copyable, they have nothing to do about it. Okay, here's another special concept that I want to talk to you about. Actually, yeah. And this is a concept called the equivalence relation. It's part of the C++20 library. I briefly mentioned it, by the way, last week in the Core CPP meetup. And let's look at it. This is a concept called equivalence relation. It defines basically a relation between two objects, T and U. And let's see its definition. So the concept of equivalence relation is basically equals to STD : relations with the exact same arguments. Okay, so syntactically, STD relation, which is a concept, is exactly the same as equivalence relation. Okay, and you can also see the note here below. It basically said that the distinction between relation and equivalence relation is purely semantic. Okay, so if I write my own class R, class T, and class U, and they all semantically and syntactically look like a relation, and I know that the semantics are such that it is an equivalent relationship, it is an equivalence relation, or it's not. There is no real way for me to actually go and tell C++, yes, this relation is an equivalence relation. Okay, this is really weird stuff, really tricky stuff. The compiler right now with C++20, as far as I understand, doesn't really have a way to differentiate between the two. If there are two overloads, two algorithms, one that is constrained on equivalence relation, the other constrained on relation, the compiler cannot choose between them. And still, it's part of the language. It's part of the C++ standard. And it's a really interesting question to try and think, why is it this way? What were they thinking, so to speak? And what are the benefits of doing things this way? And perhaps maybe how would we want to write it differently in the future? Okay, so those are like two different things that also should drive the point to you that semantics are not simple. Okay, syntax has been nailed quite correctly with concepts. Semantics are not simple, but they should be always in the back of our minds. And this leads us to basically the last slide of the talk, after which I'm happy to take more questions, of course. So first of all, concepts are great. They give us a lot of power. They're really a huge jump in the language. As I mentioned before, requires clauses can be used without concepts. Okay, and I would expect to use requires clauses much more in my code without even thinking too much about declaring or defining my own concepts. Just as you know, if you are a library writer, I would try to encourage you, and it's only my opinion, of course, to give your users power. Okay, build in some escape hatches for them to step outside the of the rails. Consider ways to do a call site customization for them to write their own class and choose between your different algorithms when it makes sense on different call sites, not just one time when the object is defined. And if I were to give some thoughts about the C++ standard and what might be improved or augmented there, I would say that, in my opinion, doing specialization on concepts is something that can be useful, can be powerful, can be sometimes required. And similarly, allowing people to do specialization on type traits, either as something that's fully supported by every compiler, or is something that compilers can choose to implement if they like, in order to I guess get better performance or whatever, is something that I think can lead to a lot of happiness within the community. So great, that's my talk. I'll be happy to stick around, of course, hear whatever comments you have, and listen and try to answer any questions. Thank you very much.
I have a question about those escape hatches.
Yeah.
Basically, as I understand them, concepts are more or less finite, made much easier. but that means more or less everything we can do now with concepts, you could have done already with finite. So why are those escape hatches a new thing?
Yeah, so I think, first of all, I would say that the concepts are not just a new type of SFINE. There are things that are very, very hard to do with SFINE, mostly regarding, I think, constraining constructors, constraining, I think, sometimes destructors even, but that's a separate topic. But one thing that the concepts do not have is specialization, okay? And because other types of SFINE had specialization, I think it wasn't as important to do those escape hatches. Okay, anyone who wanted could just specialize away whichever class or whichever specific implementation that they weren't happy with. And I'm not sure, but I think that this is the main reason why we find ourselves with these things. But I'm not sure. Any more questions or thoughts?
Hi.
Hey.
Hi there. Great talk, by the way.
Thank you.
Very informative. Thanks. If you're ever curious about questions like this, usually just posting a Stack Overflow question will get you answers from the people who really understand the decisions that were made. You usually get a pretty good explanation. I don't remember. I don't know why those decisions were made, but I'm sure a lot of thought went into them.
Yeah, thanks. I'll try to give it a go. I have to tell you that I'm actually kind of shy. I don't have like a Twitter account. I don't do what's it called, Slack or anything. But with these COVID times, I started getting more involved in the community. So I might as well, I guess, jump in and try this as well. So
sure. Well, somebody may already have asked if you haven't checked already.
Yeah, I looked a little bit at that, and I can say, by the way, for example, that this whole thing with where were we with the equivalence relation, some of it has to do just with history. Okay, many of you might know that what we now call concept is actually a short for what's actually called concepts light. Okay, way before C++11, when people were trying to formalize C++OX, there was a larger suggestion by Strausstrup to do concepts which did not just syntactic, but also some semantic checks for your classes or for your code. There was the notion and a keyword called axiom. Okay, and one could write axioms about their concepts. And the equivalence relation and the relation both appeared in that proposal with different axioms. As far as I understand, when we moved from these older concepts into concepts light, axioms were thrown away, maybe for good, maybe not. And but the two different relations remained. I think right now, obviously, you can write, I guess, maybe static analyzers that can go and look at your different objects and tell you that perhaps you can use one or the other. I'm not sure. Last week, when I presented this to Core CPP, there was a suggestion by someone who didn't see the talk, obviously, to perhaps change equivalence relation to also add like an opt-in escape hatch over here. Okay, so if one were to add like an or and some Boolean, which is always false, it could allow whoever writes their own equivalence relation to opt in and to say, hey, my relation is an equivalence relation, not just a relation. And I tend to think that they maybe didn't do it just because many relations that people write are in fact equivalence relations, and many of them are not. And it might not be so easy or trivial to consider, to think, or to force people to either opt in or opt out to everything. Perhaps they just decided let's give people the opportunity to write their own relations, call their own algorithms, and assume that they know what they're doing, meaning they only call algorithms that expect equivalence relations with their own classes that match those semantics. Thank you.
I have a question.
Yes.
So you're saying that you cannot specialize concepts, but you can specialize the traits. So a concept can be Boolean, expression of traits. So if you define a concept based on those traits, then still one of them can be specialized. So you're specializing the concept effectively.
Yes, you're very true. And yeah, I mentioned it a little bit. Yeah. The fact is that it's all possible, right? As you mentioned. But if I go and do it that way, then one might ask, why would I use concepts at all, right? If I can just work with traits, why not just work with traits? Yeah. So concepts obviously give me more power. Concepts let me use those terse notations. They can let me constrain my functions without even writing the word template, without writing the word requires. I can put it, put the name of my concept after auto, etc. So I have to use concepts in some places. But the question is, maybe to our audience here in the room, now that we go and write our own concepts, will we write our own requires expressions? Will we write our own Boolean expressions inside the concept? Or are we better to just have the concept just be equals to one Boolean and do everything else inside that Boolean just in order to give like an escape hatch? So that's a good question. I'm not sure. Yeah, but anyway, it's a potential pitfall. Right? If a library uses a concept and not without Boolean expressions, then they have no way to give this flexibility in the future.
But I would say concepts give you the way to like not repeat yourself. If you have to write number of algorithms, they all require same set of Boolean expression. Then you can easily add one and you don't have to repeat yourself again.
Yeah, I'm not sure exactly what you mean. Like, obviously, even like in-out specializations and other types of non-concept Booleans can be composed based on Boolean expressions in order to not repeat yourself. But obviously the same goes with concepts. So yeah, I definitely agree that almost anything that you can do with concepts, you can do with Boolean expressions, and one could use one or the other. And in this talk, I try to dig deep and find those specific points of difference. And I agree that sometimes they might not be too important in most cases. Okay, any more comments, questions?
Hi, hope you're fine. Do you have any simple example to show the usage of concept or require, which can be used in simple programs? I'm sorry.
Yeah, well, okay, so I can definitely, I guess I can definitely, post an example to the meetup page, etc. I think simplest example, maybe we can take from Satter's talk that we showed earlier. Let's go and try to jump into it. Wait for the animations, and here we go. Here's Herb Satter's talk.
But now let's look at templates.
Okay, so I hope that the text isn't too small for you, but we can see this. We have 3 different functions called old in, which are all templated on type name T, and they each have a requires clause. Okay, you see the one has requires on the Boolean, the other has requirements on not of the Boolean, and the third is not on the Boolean, as well as a check on the reference type. Okay, I hope this is simple enough, but not too simple of an example. Okay, any more questions or comments? Great, this has been really great talking to you, great sharing this evening with you. So really, thanks a lot.